a video here.
Okay. No issue.
Sure. As you all know, the title of this presentation is Mutual Coupling Reduction Techniques for MIMO Antennas, and we'll be having sort of an in-depth survey on it. Okay, so first of all, very good evening to all of you. Now, to begin with this talk, my outline is as follows. So first, we will discuss on the introductions of this topic. Then we will discuss on the mutual coupling reductions method, and also the basics of mutual coupling reductions, followed by what are the different types of mutual coupling reductions available, especially why we need that kind of techniques. Later on, I will show you one of the hybrid methods. Then we will discuss right from the theory to the measurement level, followed by we will show you one of the array antenna element, followed by conclusions and references. Now, to begin with the introductions, so as I go back one more time, you can see the title of this talk is on the mutual coupling reduction. So there are basically, if I break it into two parts, one you can see the first part, if I consider mutual coupling reduction techniques, that would be one part. Second part is the applications of these, that is on the MIMO antennas. So here first we would like to know that why we need that. For that reason, we have to know what is the MIMO techniques, and then only you will get to know that why we need such kind of methods. So for that, let me begin with the introductions. So now first, as you all know, the MIMO stands for multiple input, multiple output. It is an advanced technology for multiplying the capacity of the radio link using different ways of transmit and receive signals for a multipath propagation. Okay, so these MIMOs basically reported on in the early 90s. Before that, we had something like a seesaw, that is single input, single output. Now, this single input, single output system had few disadvantages as compared to the bandwidth considerations, compared to the data rate, compared to the latency, compared to the number of maximum user that one can accommodate. So based on all such cases, then we thought that, okay, MIMO would be much better than the seesaw. After that, this MIMO was extensively used in different kinds of network, as I said, to improve the channel capacity, system reliability, and the data speed. So that is basically like, if you are dealing with the maximum bandwidth, automatically your data rate will be increased. So that is the reasons why we are much more concentrating on the MIMO and MIMO communication based antennas. Next, the massive MIMO system is believed to be a key enabler of the 5th generations and 6th generation communication system. So if at present we are on the 5G communications level and we are going towards the 6G communications, both the communications, MIMO will be playing a very important role. In addition to that, in coming 6G, you will see that in addition with the MIMO, there will be some additional things will come up to improve the system reliability. Next, due to the limited space and aesthetic reason, the compact MIMO antennas are required in mobile applications. So these are the very important points, and most probably these are the introductions of this MIMO communication system. At present, we are not bothered about the mutual coupling. Mutual coupling will come over here. Now, if you are keeping multiple antennas together, what will happen? You are placing each and individual antennas within nearby. Then what will happen? The crosstalk between these two. And that is basically defined as the mutual coupling. So now as the antenna elements are close to each other, then the mutual coupling between antennas elements will be inevitable. So that's why, so you don't want something like that. So if I tell you in a very, very interesting way, that if you are dealing with multiple, say for an example, if you keep your two hands together, you have 5 fingers in the left hand, 5 fingers in the right hand. And now if you want to say for an example, if you want to shake hands or something like that, you have to keep all the fingers nearby. What will happen if you keep on reducing the gap between your fingers? What will happen? You may have, in the communication perspective, you'll be having some kind of a crosstalk. At the same time, I want that I need a maximum antennas in a channel so that I can transmit, or I should not lose any data link. So at the same time, I want maximum antennas in my system, and at the same time, I want less crosstalk between each and individual antennas. There is a challenge. So now, for that, let us first see in more details what is MIMO communications. So the MIMO communication, if you look at this particular diagram, you can see there is a transmitter, there is a receiver. In addition to that, there are encoder, modulator, and decoder and demodulator. This is for the transmitter and for the receiver, respectively. Now, this particular MIMO scenario came into the play in the year of 1987. Sorry. So in the year of 1987, when Professor Winters proposed this kind of an idea. So that he said that the efficient radio communications can take place if you can place multiple antennas together, and that will definitely improve the disadvantages that is coming from the CISO. Now, if you think about in a CISO communications, what was that? In the CISO communications, if I write it over here, if you take any CISO communications, you have one antennas, you have one more antennas, in between you have a channel. So this is a channel. Now, if this antenna is radiating, say for an example, if you send a bit of 1, this bit will go to the next antenna, to the receiver. So this is the way of communications it is going through. Now in the MIMO, what is happening? You are placing multiple antennas together. Say this is a transmitter. You are placing one antenna here, you are placing one antenna here, you are placing one antenna here. Here also you are doing the same thing. Now what will happen? Sorry. So like this, say for an example, 3 antennas are connected. Now what is happening? If you keep one over here, the one will go from 1 to here. Maybe it is 0, 0 will go to here. Maybe it is 0, 0 will go to here. So this is the way of the style of communications. Now what is happening here? In addition to that, you can have some kind of a multipath link. Say this and this particular link can be connected with this particular link can also be connected with that. Similarly, from the second antenna also, you can get such kind of link. Say this antenna can be directly connected with this, and also this antenna can be connected with that. This antenna can be connected with this. So this is the way our communications can take place in between individual antennas. So there is a very less chance of losing of any data link. That is the main advantage. Now, as we are targeting, or you are sitting on the 5G era, this 5G era demands that it has to be deliver higher data speed. It has to give low latency. It has to give us more reliability, massive network capacity. All these things should come into the 5G requirement. Now, so now for that case, if you automatically MIMO communication is preferable. So that we can produce high data speed, we can reduce the latency, we can improve the antenna bandwidth. Okay, so if we improve the antenna bandwidth, then automatically we can support large number of users. And at the same time, if you increase the bandwidth, then automatically you have to face certain consequences. Now, when you are applying one side of the MIMO communications that was said by the Dr. Winters over here is that the MIMO always give you an flexibility for the spatial multiplexing. So now when you are doing that kind of a spatial multiplexing, you will be always having some possibility of creating multiple sub channels. These are called the sub channels. Okay, so as I said, one is directly linked with this one can be directly linked with the second antenna, this one can directly link with the third antennas. So these are basically the number of sub channels you are creating. Now, what he proposed here is that these kind of sub channels, if you are using m number of sub channels, then one can have m times of data rate. Automatically at the same time, you'll be losing less information. So that is the kind of measurement, or that is the kind of communication system we are looking for. Now with that, say, if I write it in this way, so what are the communications? So first of all, these MIMO communications gives us all these four things primarily. I have already said that it can improve the signal to noise ratio. It can at the same time, it can also increase the or improve the signal to interference plus noise ratio. Both are same. In some of the book you will find SNR, in some of the books you will find SINR. Then the spatial diversity. Spatial diversity against the different signal fading, antenna beam shaping, and improve the channel capacity. You will get to know more about this kind of a spatial diversity when we will talk on the gain. So basically like that, in case of MIMO communications, you will encounter with two types of gain. One is called rate gain, one is called the diversity gain. So I will show you that what are the difference between these two and why both of them are important in case of MIMO communications. So now this is the atmosphere, this is the platform, or this is the applications where we are going to implement our antennas. Obviously, we will not be talking on these kind of thing. Okay, we will be only focusing on these. Okay, and the spacing between these two. That is the motivations, or that is the outline of this talk. Now, if we consider the mutual coupling, so now coming back to the spacing or the inter-antenna spacing. Now, if we think on the mutual coupling or the separation between two antennas, I would like to show you some of the very interesting fact. The mutual coupling in any MIMO antennas arises due to the free space radiations, surface currents, and surface wave. These are the three primary reasons which those are responsible for the mutual coupling. So now if I consider each and individual, the space radiations or the surface waves or surface current, so to some extent you can call space radiation is also a space wave. So now space wave, what are the difference between these two? Difference is very straightforward. If you work on any, or if you have worked with on any antennas, in the antennas you will have some kind of a model like this. You have a ground plane, you have a metal, that is a metal patch that is radiating your signal. So when you can get some kind of a wave that is scattered like this, or you can get some kind of a wave which is going like this. So the wave which is going like this is the surface wave. The wave which is going like this, it is a space wave. This is the simplest way one can understand these two. Now, coming back to the second case, the mutual coupling can seriously degrade the performance of the SINR that we have already discussed. But the main point here is that the question may can ask, okay, if there is a chance of SINR, so can I improve it with the help of signal processing? So, or we have to work on the circuit level to improve it. The first answer to this question is that yes, one can improve SINR with the help of some kind of an adaptive algorithm through the signal processing method. But at the same time, you may face some kind of a drawback in the signal processing method or some kind of a limitations. So it is always better to improve such things from the circuit level itself. Okay, so now you will get to know more details in the subsequent slides. Now, this mutual coupling can degrade the estimations of the carrier frequency offset, channel estimations, and angle of arrivals. This mutual coupling can adversely affect on the active reflection coefficient. So that is one of the new or interesting terms over here, because most of you are familiar with the reflection coefficient. Then what is the meaning of active reflection coefficient? The one can easily understand the active reflection coefficient. It is basically the just a second, let me write it. So the active reflection coefficient, it's nothing but a square root of your radiated power divided by the power that you supplied. Okay, so this is basically the ratio between these two. Now, the worst VSWR, that is reduces to 2 if we increase the antenna isolations to 20 dB. Okay, so there is a scope of the improvement. Now, in addition to that, if in the transmitter or receiver system, you have a power amplifier. Now, this kind of power amplifier, the multiple power amplifier, in the presence of this kind of mutual coupling, can cause significant out of band emission and creating the interference to communication system. That is also one of the reasons why we should work on the mutual coupling reduction. Now, next, in case of digital infrastructure MIMO system, the higher mutual coupling can adverse effect on the error rate and the capacity. Now, the question, let me put it in a different way, that yes, so as you are keep on saying that by using the signal processing, one can improve the mutual coupling up to a certain extent, then what is all about the signal processing method? So let me show you on that on the perspective of the digital domain. If you see that some efforts on mutual coupling mitigations have been exerted in the digital domain to optimize the MIMO communications, MIMO pre-coding and decoding scheme. It means that left and right hand side of these two antennas, left and right hand side of these antennas. Now, see what are these? The mutual coupling can be removed from the received voltage, and then the calibrated voltage can be used to compute the weight vector of the adaptive algorithms. That is one of the ways one can do it. Output SINR of the adaptive array cannot be improved by compensating the mutual coupling alone in the post-processing stage. Now, there is a bottleneck. Note that the SINR can be improved by reducing the relative noise or interference in the post-processing stage with the help of some kind of a averaging the additive noise. But the compensating the mutual coupling doesn't change the SINR. Now, the aforementioned all these techniques can potentially improve the mutual coupling in digital domain, but using the decoupling technique from the antenna point of view or from the circuit point of view, that can overcome the mutual coupling effects are more effective way. Therefore, it is vital to develop different types of decoupling method for this kind of mutual coupling reductions. So there is a motivation why you need to develop or why you want to work on this particular domain. So now let me tell you the definitions of mutual coupling. For now, coming back to the mutual coupling definitions. So the mutual coupling, it's basically, it has the capability to alter your input impedance of the antenna, to alter the reflection coefficient and also the radiation pattern. And that can be represented with these expressions. This is these two expressions can define the level of mutual coupling. So now what are these all about? CMN is what and DMN is what? These two are basically like CMN is defined the how much mutual coupling you are having, and D is the inter-element spacing between antennas. Now, with the help of this, you can get some kind of an idea that yes, mathematically, that should be the limitations or that should be the level of mutual coupling. One of the very important factor over here is that one is N and one is alpha. What is alpha? Alpha is basically the how much coupling level you are looking for. So that can be 20 dB coupling, 30 dB coupling, 40 dB coupling. As you are increasing the coupling level, it is good for you. Then what is N? N is nothing but the number of antennas you are having in your system. So this is the definitions or the theoretical way one can understand the effect of mutual coupling. Now, in practice, the mutual coupling depends not only on the array configurations, but also on the excitations of the other elements. Okay, so that is already been discussed. Now, let me tell you the basic physics behind the mutual coupling. So when you are, say for an example, the leftmost figure, this particular figure is giving you some kind of an idea about the transmitting mode, and the rightmost figure is giving you some kind of an idea about the receiving mode. Now let me talk about in the transmitting mode. Now in the transmitting mode, what is happening here? In the transmitting mode, the kind of mutual coupling is going something like that. So this is the source. Say for an example, what are these? This is one antenna, this is other antenna. They are having some kind of a separation. Consider the separation is X between these two. Now what is happening here? These nth element antennas is generating, this is the source of the antenna, and it is generating some current. Due to the current distributions on the current profile, it is radiating like this. And also because of the sum of the signal will also radiate like this. Okay, so some signal can go like this, it's like a 2, and some signal like a 3 can also go like this. Now when the three signals will come to this antenna, so this particular antenna will scatter some of the signal as 4, and again some of the signal will again go to the source of this antenna. And at the same time, this antenna, as it is scattering, so or it is rescattering, it can also have that capability to radiate some kind of a signal like this through its back side lobes. So now the entire phenomena over time, this is basically like a repetitive in nature. Okay, this is an iterative method over time. So for that reason, what is happening? The crosstalk is keep on increasing. Okay, the crosstalk between these two antennas are keep on increasing. Similar thing can also be seen whenever your antenna is working as a receiving mode. This antenna, say mth element antenna, is received some of the signal, some signal will go over here, and then this some of the signal will scattered like this, and some of the signal will go like this. Now, one antenna, whenever this particular antenna will also receive this incident wave. Now, what will this antenna do? This antenna will take the signal, and again, so this antenna is also getting the signal from this antenna, from the left antenna. So now, so this antenna and this antenna, so both the signals are being additive in nature. Okay, so basically like that, your directions of this beam will not be to your desired location. So this is the effect of the mutual coupling. A very simplest way one can understand through this simplest diagram. Okay, so this is the stage for the transmitting mode. The rightmost stage is for the receiving mode. So, and you can see that crosstalk is keep on increasing over time. So you have to give something to your circuit so that the crosstalk can be minimized. Okay, so this is the way one can think about it. Now, let us begin with what are the different techniques are available. Say, if we consider that, yes, I would like to I would like to reduce the mutual coupling for the applications of the MIMO. If you consider that for the MIMO antenna design, there are different methods. One can take a printed antenna, one can take a DRA, dielectric resonator based antenna, one can make a reconfigurable antenna, metamaterial based antenna, irrespective of whatever be the antenna. I can write 3 more antennas here also. But irrespective of that, the main thing, if you are working towards the MIMO, your main thing is the mutual coupling reduction techniques. What kind of techniques you are going to use? For that reason, there are different techniques. First technique is one can use something like a complementary split ring resonator, use a defective ground structures, some kind of a decoupling network, something like a EBG, electromagnetic band gap structure, neutralizations line, something like a parasitics or slot elements. So these are the techniques that can be used to reduce the mutual coupling. Now, coming back to the actual phase of this particular talk. So now you know why there is a requirement of the MIMO communications. First, that was the first thing. Second, you know why we have to reduce the mutual coupling effect in the antennas. If you know if you are convinced with this particular thing, then what are the different techniques on the mutual coupling reductions? So these are the different techniques. Now I will give you the glimpse of each and individual, and I will focus more on a particular technology or particular technique so that your things will be, or the concept will be much more clear. Now, let me begin with the first thing, that is how to improve the mutual coupling reductions using a defective ground structure. That is called DGS. What is DGS? DGS is basically nothing but a defective ground structure that will represent the defects or slot integrated on the ground plane of any kinds of planar circuit. Giving you 2 examples. This is first example, this is second example, and this is third examples. Now, the first example, let me talk about more on this. In the first example, it was proposed in around 2017. So here, what is happening here? You can see there is one element antenna, there is a second element antennas, and in between they are putting something like on the back side of the ground, they are putting something like some slot. Slot means there is no, the white portions, in the white portion, there is no metal. In the blue, so that is the way it is making something like this. Now, what is PGDS? It is PGDS. It basically stands for, it is nothing but it's a periodic S-shaped. You can see that it's something like, it looks like an S, periodic S-shaped defected ground structure. Now, this structure, it has been placed between these 2 radiating elements. Okay, and idea is to reduce the mutual coupling. Now, what is happening here? This PDGS, it will interrupt the EM far field significantly, and that will induce some kind of a current between these elements. And at the same time, if you keep the coupling of these two antenna element, you know that the coupling between these two antenna element, it is basically a functions of their relative alignments between these two antennas. If you do not put this PDGS, what will happen? If you do not put this PDGS, then the large surface current will introduce on these coupled antennas elements, and that will result in the mutual coupling. It's a very straightforward method. This is one of the method. In the second, there is one method called something like SR-DGS based MIMO antennas for mutual coupling reductions with top layer and the ground layer of the DGS. What is going on here? This is a top level of the design, and this is the ground level. In the ground level, they put one kind of a slot that is act as a DGS. And this is, again, it is all DGS are named like a shape of the structure. And you can see it is a SR DGS, stands for the square ring defected ground structure. SR stands for square ring defect. Okay. So now what is happening here? This part is also very interesting. So here, what is going on? There are basically, you can see there are two ports in the. So before that, you can consider it, there are two patches. One is this patch, okay, in the center, and in the outer periphery, you have one more patch. Now, in that center patch, you are keeping P1 and P2, okay? And in the outer patch, you are keeping P3 and P4. What is going on here? So here, before that, now, what is happening here, you can keep one also in the back side, you are keeping a structure something like this. Now, for time being, we are keeping it side by side, but actually it plays in the back side of this antenna. Now, what is going on here? So now here, your inner, if you consider this is the inner patch, this inner patch, you are feeding the signal at P1 and P2, and the feeding OS are giving you some kind of an orthogonal mode. For this particular case, P1 is giving you some mode like TM01, and this P2 is giving you some mode like TM10. At the same time, if you are using the P3 and P4, that is the outer ring, that will give you some more higher order orthogonal modes. So why I'm saying higher order orthogonal modes for these two, the mode should be around, for say, this is for P3, it is TM21, for P4, it is TM12. So now, if at the same time you are having these kind of a square ring. So what square ring is doing it? This will act as some kind of a resonating slots. Okay. And this resonating slot will substantially reduce the surface wave, and automatically that will decrease the cross polar level of your antenna. Okay. So you are basically confining the entire signal within the dielectric that can cause some kind of a decoupling between the antenna and the radiating elements. So it is basically acting as some kind of a resonating slots. Now, third part, I'm not going into the details of it with the interest of time. So here also, this is one of the methods. It's called using some kind of a T-shaped metallic strip that can be used to improve the mutual coupling. Now, going back to the second stage, how the CSRR, a complementary split ring resonator, how these CSRR can improve the level of the mutual coupling. So now there are different ways of doing it. Okay. So first of all, what is CSRR? CSRR is nothing but it is a periodic configurations of some kind of a metallic ring or some kind of a shunt strip or some kind of a capacitive gap that can be termed as a CSRR that is used for the filtering applications. So let me tell you some kind of a brief story about CSRR. CSRR actually initially developed due to some filtering applications. CSRR was invented for the filtering applications so that one can make a very nice planar filter. Later on, the researcher thought that the CSRR can also be used in kinds of a planar technology like antennas. Okay, then the motivation began, and now here in this case, you can see this is one antenna, this is one antenna. They are calling it as something like a triangular, semi-triangular shape of antennas. Okay. In between, you are keeping some kind of a stuff followed by some kind of a CSRR structure. So now this CSRR structure, what it is doing, it is basically giving you some kind, it is, you can see that it is giving something like a LC tank circuit. It means it will have an inductor and capacitor. Now this, it will give us some kind of a LC tank circuit. And what tank circuit generally used to do? So if I place one inductor and one capacitor like this, so now, and I'm saying that it works as a tank circuit. Now with the antennas, if I put a tank circuit over here, what it does, this tank circuit automatically or inherently, it can store some of the energy at a lower frequency. And at the same time, it will block some of the currents in the ground plane to reach to the other, so that that current should not reach to the other antenna elements. One more time. So this LC tank, what it does, it can store energy at lower frequency, and it can also block the current in the ground so that it is ground to reach the other antenna elements. Okay. So the current should not be go to the other element antenna, so that you can make some good mutually decoupled antennas. Okay. So basically this kind of a CSRR structure that is been generally used to prevent the current flow between the antenna elements. That is the main reason. Okay. Now, one of the other way one can see, you can see that this is also one of the structure where you have a CSRR ring at the ground plane. Then that will also improve the mutual coupling. This is a very, very good example for that. You can see they put only one CSRR ring between two antennas. So these are the monopole antennas are being there. So now these two monopole antennas on the other side and on the ground side, you have something like a CSRR structure. So these structures give you some kind of a resonance. At that particular resonance, there will be a very high impedance, ideally infinite impedance. Automatically, the current won't travel from this antenna to the other antenna. That is the simple topology. Okay. So now coming back to the next category is the neutralization line. What is neutralization line? This is also one of the ways one can improve the mutual coupling. So now you can see the neutralization lines are basically used to pass the EM waves from one antenna to the other through some kind of a metallic slit or some kind of a lumped element. Okay, the neutralization line concept is very interesting. You are basically showing the current. So there are two techniques. First technique is that you can think it in a simplest way, that we are showing the current to a wrong directions so that it will never reach to the second antennas. That is one way. Second way is that you are telling your current to go to some path which will take a longer time of propagation. Okay, so these are the neutralizations line, or in some of the textbook you will find neutralizations effects. So now in the so there you can see two examples. This is first, this is second. Now both these techniques, in both the cases, the neutralizations lines are very interesting. So this is basically here what you are doing it. If I take an example of the first case, that is the figure A, here we are keeping the neutralizations line between these two antennas. They are placed some kind of an orthogonal. So so here what is going on here? Here it's basically like this is port 1, this is port 3, this is port 4, port 2, this is port 4. So this is a complete technique over here. Now what is going on here? Now this is a 4-port antennas that is a consist of something like a circular monopole antennas. That is the first thing. Now the two ports, if you consider port 1 and port 3, two ports are mounted on the upper side of the substrate, and this side is basically, it is on the lower side of the substrate. Okay, so now you can easily connect it, right? So this is the top face, this is the bottom face of the substrate, and all these antennas are basically on the top side. These two antennas are in the bottom side. You are connecting the connectors, and there are 4 ports. So this is the techniques. Now all these four radiating elements are, needless to say, they are orthogonal to each other. Now the partially the ground plane, whatever they are having, this partial ground plane with a very, very small rectangular slit or slot you are introducing just to improve the bandwidth. Okay, so something like you can see that. So something like some slots you are introducing just to improve the bandwidth. Remember that whenever you are targeting for the MIMO applications, bandwidth is also important. You should not talk more on the mutual coupling. At the same time, you should also look into the bandwidth improvement. Okay, so if you do not get the good bandwidth, then there is no point of getting it in the 5G communications era, and if you are targeting for a MIMO communications. Now, these kind of a neutralizations line over here, it will act and give you something like a multimode resonating effect. Okay, so that because of the multimode resonating effect, again, what will happen, some of the things exactly it will work as like the CSRR ring. It will give you some kind of some resonance so that the current will be blocked. Okay, so this is also one way of doing it. Idea is something like that. On the same phase, you are keeping the slot. In the CSRR, what you had two antennas on the other side. In the back side of the ground, you are keeping one resonant tank that is in the form of CSRR that you did in the last case. In this case, on the same plane, you are keeping some line so that you can get something like a good coupling between antennas. Here, these particular lines is helping you to get very less crosstalk or very good mutual coupling between these two orthogonal antennas. Okay. Now, fourth case is the parasitic or slot elements. I'll quickly go through it. It's very simple. So here, what are you doing here? Here, basically, you are keeping all four antennas for obviously for the MIMO applications. All these four antennas, you are keeping some kind of a making some kind of a slot over here, and all these slots are basically helping you to get some kind of a resonance effect. One more time. So now this is basically like you can see that this antenna is radiating something like this, and this is basically giving you some kind of the mutual coupling. In this particular case, it is mainly reduced due to the asymmetrical structures. Okay, and the radiation pattern and the automatically the radiations pattern will be improved, or the mutual coupling will be reduced due to this decoupling method. Okay, so now also this is one of the ways the parasitic slots will help you. Now there are different ways of shaping these kind of a parasitic slots. Okay, slot means there is no metal. White portion means there is no metal. You're creating some kind of a slot. If you might have designed some kind of something like a aperture coupled antenna, you might have seen the same thing there. Now, after that, that is the EBG, and this is the technique that we are going to mainly focus on this class. So now this particular technique that is called electromagnetic bandgap structures. So now these electromagnetic bandgap structures is basically giving you some kind of one of the ways of reducing the mutual coupling. That is the first thing. Before I start the EBG, as of now, we had studied 4 different types of techniques by which one can reduce the mutual coupling. EBG is the 5th one. Now, here we will be spending more time on the EBG, and we'll show you that taking one of the examples or one of the techniques, okay, how to design or how to get a good mutually decoupled antennas for MIMO applications. Now, first of all, what is EBG? EBG is basically like an electromagnetic bandgap structures. Now, let me tell you something like why these EBG structures came into the play. So now EBG structure, as you see, the EBG structure is giving you something like some artificial magnetic conductor. We are making some kind of a conductor which is artificial in nature and which is giving us some kind of an excellent performances. Now, this EBG can give us something like a very, very special thing, that it is, as the name suggests, it is giving us some kind of a band gap in nature. As the name suggests, band gap structure. Okay. At the same time, EBG will also give you something like called in-phase reflection. Okay. So the in-phase reflection phenomena that can be achieved from the EBG. Now, if you see this is the figure 1, it is showing you something like a 3D volumetric views of some kind of a structure that is like EBG. This particular structure, it is a 2D planar EBG structures, and this is 1D transmission line type EBG structure. Now, this structure is also as very, very well known. It is called mushroom type EBG structures. What is basically like this? All these black dots are these. First of all, the shape is hexagonal. You are keeping this hexagonal shape over a same periodic manner. And now in between, you have some kind of a metal post. So if I draw the structure, if you see the side view of this, you will see the side view something like this. You have a metal. Just a second. Let me. Yeah. So you have a metal. Then you have also a metal. And this is also a metal. Again, you have a metal. You have a metal here. You have a metal. This is a periodic in nature. Okay. Hope you can follow this diagram. So as I said, these black spots are basically something like a metal post. Okay, so all these metal posts are being separated with a equal spacing. Okay, and now this kind of a spacing is basically, if you look at in the side view, what is giving you the very, very interesting phenomena is happening here. Now, what is this interesting phenomena? So now if you select any one cell, say for an example, if I select this particular cell, what is giving us in terms of Ln and C, inductor and capacitor? It will give us, say there is a current flow over here. So because of this path, you will be getting some kind of an inductor. And because of this separation between these two metal over here, you will be getting some kind of a capacitance, right? So you'll be getting something like that. Now, if I quickly write the impedance of this particular structure, simplest way, I can write it like Z is equal to, obviously Z is a function of omega. This is nothing but you will be having J omega L divided by 1 minus of omega square LC, right? And obviously the resonance frequency F naught would be 1 by 2 pi times of root of LC, right? Now you understand that. So obviously this is giving us some kind of a resonance frequency. Okay, so some F naught is giving. So now what is going on here? If you know that if I consider and if I say this EBG will give us something like a artificial magnetic conducting nature. Okay, it is artificially made and it is a magnetic structure. So and it is a conductor. So I'll be calling it as an artificial magnetic conductor. Fine. Now if I compare this thing with the say for an example, if you take any perfect conductor, perfect electric conductor. So now if I give a comparison between PEC and AMC, what are the comparison? First thing one can easily say, okay, if as it is a perfect electric conductor, the impedance will be 0. Automatically, as it is a artificial magnetic conductor, its impedance will be infinite at resonance frequency, right? At resonance frequency, this if you consider it, if you look at these expressions, your impedance will be infinite. Now, so obviously, as it is a periodic, as it is a perfect electric conductor, automatically it doesn't support any electric field inside the conductor. Fine. Now, what would be the next case? Next case one can consider, if you are dealing with any perfect electric conductor, it will reflect all the incident energy with something like a phase reversal, right? So that will give you something like a 180-degree reflection phase, if I consider. Okay, 180-degree reflection phase. And at the same time, this AMC, it will give you some reflection phase, or I can say phi, reflection phi will be 0. That is a very, very interesting thing. So now one can say that what would be this phi? Phi, we can define it something like a imaginary part of natural logarithm ln ER by EI. Simple way one can define it. Okay, imaginary part of the natural logarithm ln ER by EI. Okay, so this is the simplest way one can define the reflection phase. Now, what is happening there in this particular case? If you look at the reflection phase in this EBG structure, if you see that, if you write the reflection phase with the frequency, so in this case, your reflection phase will be something like this. Okay, and at the resonance frequency, your reflection phase will be 0. This is your F naught. Okay, so this is the way this kind of EBG structure works. Okay, so now this is the basic difference, because you can always relate it with perfect electric conductor. So that's why I intentionally said this, so that you can understand the difference between the EBG structures followed by the your artificial magnetic conductors or EBG structures. Is every AMC or EBG, whatever you will call it. Okay, so this will give you something like a high impedance surface. That is the reasons why, because at the high impedance surface, at the high impedance, when it is happening high impedance, when this your impedance will be infinite, when this impedance will be infinite, when you will encounter with the resonance frequency, you can see these simplest expressions. When it will give you the get the resonance frequency, then only you will get the perfect reflection, I mean high impedance or infinite impedance ideally. And what will happen at infinite impedance? Your reflection phase will be 0. So this is the way one can easily think about it. Okay, so now if you consider it, so now what will happen? So when in electromagnetic waves, we are always dealing with either the wave is TM mode or TE mode. In general, what happened, one of the very interesting thing is that if you look at the impedance in a little bit of detailed manner, so here if you call it as an impedance, and if you see the frequency, if you look at the impedance, how will you see the impedance? If it is a 0 scale, then you will see the real part of the impedance. Let me take a different color. So I'm spending intentionally a little bit more time so that you can understand the basics of it. Okay, so now if I consider our real impedance, it would be something like this, correct? And automatically, if you look at the imaginary part of the impedance, how it will look. The imaginary part of the impedance, it will look like something like this. I hope all of you know this. So, okay, something like that. So red portion is the real part of the impedance. Imaginary portions is the imaginary part of the impedance. And obviously the x-axis is the frequency. Now here the TM, so one more thing, what I said, that can be a TM and that can be a TE, transverse electric, transverse magnetic. Now remember, always remember, this TM always support the TM waves or the what is happening here. So first thing that you have to understand that what EBG is doing it over here. So if you defined an EBG structure, say for an example, let me take this example. So here by making something like some structure like this, and I'm calling it, it is working as an EBG structures, and it is giving us some kind of an infinite impedance at resonance frequency. At the same time, my reflection phase will be 0 or in phase reflection. Okay, so now I am keeping these two antennas. This is one antenna, this is one antennas, and in between I am keeping something like that. And I'm saying that, okay, this is my feeding point, this is my feeding point, and I'm saying that these EBG structures is helping me to reduce the mutual coupling. The question is how now? So now you know the understanding, you have a basic understanding of the EBG through all these expressions. Now we are discussing on this. Now we are keep on saying the surface wave and surface current. Now here what EBG does, or any kinds of high impedance surface does, they are basically helping you to reduce the surface wave. Okay, now the question is how? See, the surface wave can have two properties or two ways. One is that surface wave can support the TM surface wave, or other one can be a TE mode surface wave, or in a way transverse magnetic surface wave, transverse electric surface wave. If you deal with the transverse magnetic surface waves, these waves are basically supported on inductive surface. And TE, that is the transverse electric wave, that are basically supportive on the capacitive surface. Now, coming back to this resonance, coming back to the impedance things, what is happening here? When you will get, so at resonance, so if you look at the resonance curve, so before the resonance, you will be having a TM mode, TM surface wave mode. After the resonance, you will be having a TE mode, because after resonance, capacitance will be dominating factor. So before resonance, TM mode, after resonance, TE mode, and at resonance, infinite impedance, purely resistive, right? So this is the reason why these EBG plays an important role to reduce the surface wave. Okay, so this is the basic physics behind it. So hope you have understood the concept. Now let me go to the next phase. Okay, so now we proposed one of the EBG structures I'm showing you over here. So now this EBG structure, first thing you would like to see the performance of the EBG structures with the help of something like a dispersion diagram. So this is called the dispersion diagram. Here you will be comparing your modes with the light line. You will be seeing your first mode and the second mode. In between first mode and your second mode, you get some kind of a gap. That gap in terms of frequency will give you some kind of a band gap. The idea is that over the band gap, you will be getting ideally infinite impedance. Okay. Now, so here the design principle is something like we propose something like a structures which is having a sandwich between two different dielectric constant based substrate. One is FR4, one is TLY5 substrate, and in between you are making something like a meta surface. And this is the way. So this is the way one can generate some EBG, some electromagnetic bandgap structures. So the main important idea of presenting this, that this shape can be any shape, make your own shape and get the bandgap structures. Important thing is that the concept behind these bandgap structures. Okay, so with this concept, then we developed this kind of an EBG structures. These EBG structures performance is good. And it can, and you also know, and if I say EBG can reduce or the surface wave coupling, you also know the reason why it is being so. Now, then what we did some analysis, some circuit model analysis, followed by some, after that you can see that we are keeping the EBG. And one of the beauty of the EBG is that if you place the EBG structure in between two microstrip line, then what will happen? It will show you something like a band stop nature. That is the reason why EBG is a very good. So now here we are talking about the EBG for the antenna applications. For mind it, this EBG can have a multiple applications. EBG can be used for the antenna gain enhancement. It can be used to get some reconfigurations. It can obviously it can be used for mutual coupling reductions. Then EBG can also give you something like a band notch characteristics. If you are designing any band notch antenna, that it will give you a sharp S21 down to the DV level. So that can also be done with the help of EBG. In addition to that, EBG will also give you something like a bandwidth enhancement. Okay, there are different, so EBG can give you lots of advantages to your structure. Now, here our target is to reduce the mutual coupling. That's all. Now, you can see the first we saw this, and accordingly we make the equivalent circuit model of this, and I would like to see that how much S21 you are getting it from here. So because we are targeting for the mutual coupling reduction, so we would like to see what would be the band notch characteristics because of this EBG structure. Here the thing is that you have to see without the EBG and with the EBG. Without the EBG, you will get a simple capacitance between these two metal line. With the EBG structures, your equivalent circuit model will change. You can see that the blue lines indicates the exactly equivalent circuit model of this. And the simulated and equivalent circuit model both are validating up to a reasonable extent. Now, after that, let me go to the next part. After that, what we did, we concentrated on the antennas. We developed one antennas. So this is the feeding techniques. The kind of feeding technique that we used, that is basically like a substrate integrated waveguide technology. Maybe one lectures we will spend on that. What is the substrate integrated waveguide techniques? So now this here we are basically giving some kind of a signal feeding, and after that the signal feeding will be based on something like a microstrip line. Then it will convert it to some kind of a waveguide modes. Okay, because you know that microstrip line is basically giving you something like a transverse electric mode, TEM mode. When it will reach to that waveguiding structure, it has to support TE10 mode. So that kind of a mode separations or mode transition should be there in your structures. In between, you can see there is a one element antenna is placed over here. Things were fine. Then we got some kind of a good matching performance, and it was optimized extensively. And this particular antenna is basically what we are targeting at 28 gigahertz. You all know that 28 gigahertz is a very, very well-known frequency for a 5G communications applications. Now, after that, we saw the different kinds of radiation patterns for the E plane and H plane. Not spending time. So if you have any doubts, I will say on this. Then we discussed on the, we saw that what would be the surface current distributions on this kind of an antennas. So we can see. So quickly I can tell you this is the electric field magnitude propagations. So here what we did, this is the entire structures. Okay, this is the one input, this is the other input. In between we have two antennas. So let me again show you the structures one more time. So here we have two antennas side by side. Okay, you can see this is one antenna, this is other antennas. Two antennas we are side by side. In between we are having the EBG. This is without the EBG what is happening, and this is with the EBG what is happening. Now let me tell you what is happening here. So now if you look at the electric field patterns, here what we did, you can see some kind of a coupling, signals is being coupled. So if we keep the EBG, however, we have a drastic reductions of the signal that is being coupled from this port to this port. However, you can see some kind of a propagations of the signal is happening from this port to this port. How to reduce that? One more time we thought that what will happen at the center if we place something like a defective ground structures. So now we place a defective ground structures at the center, and that is what is doing, that it is drastically reducing. See, there is no signal is propagating from this port to this port. So this is the way ideally it is giving us a very good mutual coupling. Basically this antenna ideally it is having infinite dB of mutual coupling. Okay, because from the simulation you can see all the blue spot. It means there is no signals is coming from this antenna to this antenna. So they are highly decoupled. Now after that, we fabricated these things. I am showing you that there are two elements antenna. This is one antenna. This is one antenna. It's a simple patch antenna. Look at how the signal fading is going on. Okay, so the signal fading is very, very complex in nature. You are feeding the signal, then the signal is propagating, and again, so there is the signal is propagating through this patch, then the mutual coupling is happening. So it is, you can see this is the top layer, this is the middle layer, and this is the bottom layer. So this is basically a sandwich of 3 metal layers indeed. Okay, so now after that we developed these antennas. This is the fabricated image of these antennas. Then we checked the performance, each and individual things of these antennas, and then this is the overall antennas. You can see the photographs of it, and we have compared it with some 5 rupees coin just to show you the size of this antenna is very, very less. After that, this antenna, the most important thing here is that you can see the isolation is around 71.9 dB, close to 72 dB of improvement that is happening at close to 28 gigahertz. And if you think in terms of, if you are planning to commercialize the product, you have to see in terms of 5G bandwidth. Okay, 5G range bandwidth over center at 28 gigahertz. Over that bandwidth band, the isolation is very good, 32.7 dB. Talking about the measured result, not the simulation. Okay, so, and of all these FTBR, there is front to back ratio of these patterns. It's also good, 19.8 dB and 27.1 dB in the simulations. So now, after that, then one of the very important thing, as we are keep on talking on the mutual MIMO and MIMO. So in the MIMO communications, one of the very, very important thing is the envelope correlation coefficient. Whenever our product is ready. So now once the product is ready, then when you are targeting for the applications, then you have to fulfill each and individual parameters of that for that particular applications. One of the parameter is the envelope correlation coefficient. What is that? The envelope correlation coefficient is the relationship between the incoming signal at the ports of the MIMO or any antenna or any array antennas. So the envelope correlation coefficient will give you the quality of the communications what we are having. Okay, so now whenever you are defining the envelope correlation coefficient, that is for that case, particular case, you are basically defining your system characteristics or your system performances. Okay, so now for any kinds of envelope correlation coefficient, so this, if you are targeting for a MIMO applications, this ECC calculations is very, very important. The reason is that in MIMO communications, one of the very, very important term is the antenna correlation coefficient, that is ACC. So now to get the antenna correlation coefficient, you have to know the envelope correlation coefficient. Okay, so you know that the correlation coefficient can be based on the power, can be based on the signal, can based on the envelope. Okay, so now these are the different correlation coefficients are available. But whenever you are talking on the MIMO communications for an antenna specific application, then ACC plays a very important role. ACC is a very straightforward way you can calculate. If you have the ECC data, root of ECC data will give you the ACC. Okay, now the point here is that whenever you are talking about such kind of a system scenario, so you want to measure the ECC for that particular case, higher the values of ECC, it will lead to the higher correlations and mutual coupling. So it indicates that you have to have very low mutual coupling or high in dB of mutual coupling, so that your ECC can be reduced drastically. Now, once you have the antenna, you can also measure the ECC. There are different ways of measurement. One is S parameter method, one is far field method, one is S parameter and radiation efficiency method. So let us discuss a little bit on this. The first method is the S parameter method. There is a dedicated equations for that, and it is one of the very simplest method. In this case, basically, you are basically dealing with the reflected signal. Okay. So you are basically dealing with the reflection coefficients of the signals and getting the parameters from your measurement, putting it in these expressions and getting your ECC value. And this method is a very fast method. Okay, but the problem here is that this method is simple and fast method. But the problem here is that this S parameter method, sometimes it estimate the inaccurate values of ECC. Okay, due to higher lossy properties of the printed antennas. And also this ECC, this method, it is generally used for the highly efficient antenna, which is having efficiency of greater than 90%. That is theoretically proven. Okay, so one of the other way one can do it, once you measure the radiation pattern, far field radiation pattern, from there, using these simplest expressions, you can also measure the ECC. Okay, so this method is uses your pattern that you have taken from the azimuth and from the elevation plane, and then you put these values on these particular expressions, and you can get your ECC. And this ECC method, this particular method is most accurate method, and it will give you some kind of an exact values of ECC. After that, you know the method, so technique is known to you. Then we did the same thing for the ECC. We calculate the ECC from the measurement, and then we define the ECC for this particular case is 0.00015. That is a very good number. And after the ECC, once your ECC is known, then the next thing is the diversity gain, next parameter. Okay, so I told you that diversity gain plays a very important role. Whenever you are talking on the MIMO communications, diversity gain plays a very important role. I told you there are two types of gain. One is called rate gain, one is called the diversity gain. Now, whenever you have a multipath connections in the MIMO communications, and if you compare between the any kinds of CISO communications versus the MIMO communications, the diversity gain plays a very important role. Why? Diversity gain will give you some idea about or some informations about the probability error. In communications, the probability error plays a very important role. If you think about any kinds of a CISO communications, or if you think at the same time, if you think in terms of MIMO communications, now you can define for these two communications technique, you can define the probability error for this particular case. You can define it with 1 by of SNR or SNIR, whatever you say. Then for a MIMO communications, this probability error can be defined. Look at it over here. SNR to the power of diversity gain. Now, hence, see, the 1 by SNR to the power of diversity gain. So the probability error, you are drastically reducing the probability error in the case of MIMO communications. Now, next is that then it should be you should get a very smart values of DG, that is the diversity gain. So now the diversity gain gives about an idea about the reliability of a MIMO communications. In the beginning, we said the MIMO gives a good reliability. Why? This is the reason. The higher values of the reliability gain, the isolation is better. It is dependent on the correlation coefficient between the antenna signals. How can you represent the diversity gain? 10 root of 1 minus of ECC square. Hence, the ECC is a very, very important number. If you have a very good, very low values of ECC, automatically look at your diversity gain, it would be close to 10, that is 9.99. Okay, so this is the way. So you can 1 by SNR to the power of 10. Okay, and that is the difference. This is 1 by SNR and this is 1 by SNR to the power of 10. That is the way. So that's why, and why you are getting a good number, because your ECC value is very good. Okay, so this is the way one can define the diversity gain in a simplest manner. It has more details into that. I'm not going into that level. Now, after that, we also check the antenna efficiency. I'm quickly skipping this slide for the interest of time. Then again, one of the important point is the channel capacity, that also it was being divided. It was being measured. And then finally, what we did, we developed one just to check what will happen if we keep the same concept for just to make a 4-element array. Right now, we have demonstrated with a 2-element array, right? Now, what will happen if you place one more array and you just have a 4-element array? Why you need that? Obviously, so for an example, if you think about any kinds of say for an example, what would be the reason for that? Say, if you haven't first, what was the procedure? If I write it over here, first is you have to develop the antenna. Once you have developed the antenna, you add something like say for an example, some kind of a parasitic in the antenna. That can be in the form of a DGS, EBG, something like that. Okay, so that will give you some kind of an additional improvement, like a bandwidth enhancement, say for an example. Now, if you have to support the high data rate for any kinds of 5G network, you have to move from the single element to the dual element. Okay, so for that reason, to accommodate the high data rate, so up till now we are talking on the dual element. Now we are, after getting a good performance from the dual element, we are motivated to design some of the higher element model. Okay, and that higher element model, one can make it in a linear array configurations, or you can make it in a orthogonal array configurations. Okay, so we have made a linear array configurations. You can see different parts of this, and finally see how complicated it is. So now we are keeping all these things bonded with some kind of a shouldering wire, and then finally we got this antenna. So now this antenna gives us a very good performances. So this antenna, obviously it is working in between this 5G band, and then this antenna giving us a good standard gain of 13.3 dB. Okay, and finally we have put it in the case of performance comparison, where you can see the performance is being compared with all the reported work, where you can see there are some of the methods I have already suggested. So some of the method is called the coupled line resonator. Then we have discussed with CSRR. Then we discussed with DGS. Then we discussed about something like a hybrid isolator in the form of neutralization line. So there are absorbers by which you can improve the mutual coupling. This table is preferably showing you the effect of the different ways one can get a good mutual coupling reduction. You can use the different types of absorber, polarization converters. So many things can be used. But in some of the cases, like reference this particular work, they use EBG plus SRR, EBG plus DGS. We also use EBG plus DGS. You had seen that. Okay, this particular thing is basically called hybrid method, hybrid decoupling method, because you are adding two methods together. Okay, so that is just to show you as a conclusion, just to show you what are the different ways one can get good mutually decoupled antennas. Okay, so these are the ways one can make it. CSRR also, and some of the meta surface means something like a close to AMC. Okay, so in the just let me tell you that this meta surface is basically like it has actually come up from that era, from that artificial magnetic conductor era. Okay, so now if you consider any kinds of a, say for an example, say if you are talking about any kinds of a any AMC that can be defined in, or any artificial magnetic conductor that can be defined, it either you have a negative epsilon or positive negative epsilon, positive permeability. That can give you some kind of a single negative structures. Then you will have a both of them negative. That is called DNG, double negative structures. Then you can get a double refractive index, DRI, something like that. Okay, or sorry, not double, negative refractive index structures. Okay, so and then you can also get something like a metamaterial. So there are different ways one can define this kind of a structure. Now, with this, I would like to conclude it. In this particular, here we have discussed different type methods of mutual coupling reductions. You know that why you need the mutual coupling reductions for the MIMO applications. You know that what are the once your antenna is ready, then you can check for the what would be the how to improve the data rate by making by increasing the element arrays. Okay, then we talked the element arrays performances also we discussed. And finally, this entire thing is, we have published one paper recently in the IEEE Access. Whatever I presented, in the title of this, you can check it in the internet. This is an open access journal. You can read this paper. You will get more details about it. Okay. So these are the references, key references. And finally, I would like to acknowledge my PhD student, Shomik, who has mainly invented these structures. He is doing PhD in my group. Also, I would like to thank Science and Engineering Research Board for funding us for the RF anechoic chamber and MMIC lab at IIT Palakkad. Also, I would like to thank Indian Space Research Organizations for giving us a fund to do some meaningful research. So thank you so much. That's all from my end. And at the same time, I would like to thank IEEE Malabar Hub and IEEE Student Branch Chapter IIT Palakkad, also the Malabar Subsection, for giving me this opportunity. And if you have any questions, feel free to tell me.
Participants, if you have any queries, you can just unmute yourself and you can ask directly with the speaker.
Hello, good afternoon, sir.
Good afternoon.
Sir, I'm Srirag. Okay, so regarding these electromagnetic band gap structures, is it always necessary to connect this upper layer and ground plane together for electromagnetic band gap structure? My question is like this: we have a patch on the metal patch on the upper surface, and we have a ground on the lower surface or substrate. So, is it for all electromagnetic band gap structures, we will use some wire to connect? Is it like that, or some planar?
No. See, this is one of the ways you can make the EBG. This is called the mushroom type EBG. There is a uniplanar structures are also there. Okay, so there, see, in this, the best example of our example, right here, what we did, if you look at our EBG structures, okay, so these EBG structure that we proposed over here, it is not any ground plane connections. It is on the one face of the line. If you can see the structures, okay.
Okay, but okay, sir. But some holes are, I can see some holes on the.
No. These holes are basically like I didn't discuss it for the interest of the time. So these holes are basically like creating some kind of a wave guiding structures. Here, actually, if you look at this entire thing, if I show you the fabricated here, see, you can see that these waves are basically acting as a transmission line. It's like an wave guide. Right. Okay. So in metallic wave guiding structure is what? It is basically like you have a metal box, something like that. Right. This is you can also make some wave guiding structures or which will behave as a wave guide by making some kind of a, say, on the PCB. On the PCB, what we'll have? You have a ground plane, you have a metal over here, right? Okay. And you have also a metal over here. Now, in between, you are creating some kind of a metal post. Okay. Consider it as a side view. Okay. So now the metal post on the both side, you can see there is also a metal post. This is also a metal post. Remember that. So this metal post is basically like they are having a very close separation. Now it will act in between. It has a dielectric, right, from the substrate. Okay. So now you can imagine, right? The wave can pass through like this. It is actually behaving like an wave guiding structure. You have in the left side, you have a metal, in the right side, you have some kind of a metal, and in between you have a dielectric. Okay. So it is basically a transmission line. It is not an EBG.
Okay, okay. Thank you, sir. Okay.
Okay.
So I think no more questions are there. And the section was very excellent, covered different aspects of mutual coupling with respect to MIMO antenna. Sir has given several techniques for reduction of mutual coupling, like DGS, CSRR method, neutralization line, parasitic method, EVG. Then also given a hybrid form combining EVG and DGS. And last, he had an example with a 4-element antenna. I believe all the participants who have attended this might have gained information regarding mutual coupling reduction. On behalf of IEEE Malabar Subsection and IEEE Malabar Hub, I would like to thank Dr. Sukomal for spending 1 hour with us to have a discussion on mutual coupling reduction techniques in MIMO. Thank you once again, sir. So hope we will have a meeting soon later.
Yes, thank you, Mr. Savik, for inviting me for this, and I hope that student or participants, whoever is present over here today, they might have get benefited, or
Yes,
something you got to know today. And important thing is that there is a chain reactions. Okay, so you have to start from there, and you have to understand the background physics also. Everything is important. Okay,
yes.
so, and if you have any questions, feel free to email me. My email IDs are displaying over here. So thank you so much once again.
Thank you, sir. Thank you, sir.
Okay, so shall I leave?
Yes, sir. Yes, sir.
Thank you.
Yes,
Thank
sir.
you. Thank you so much.
Thank you.